So we're going to continue with the topic of yesterday's lecture. Let me remind you what it was. So we had some matrix with n rows and p columns. Well, we want n to be typically much less than p. We have a vector. So this is a known matrix. We have a vector which is an RP and unknown. And we have we assume that this vector here in Rn is known. And the goal of compressed sensing is to find ways to invert the system, right? Computationally efficient ways. Well, I actually need to say a few more things about computational efficiency. If you remember, so yesterday essentially what we did was the following. So we introduced two problems. I mean, there's the L0 problem, the zero norm problem, and there was the L1 problem, right? Okay, so if you take a vector, L0 is a number of non-zero coordinates. And the L1 norm, well, it's just the L1 norm. And we had two problems. I'm just going to write them. As a single problem. Right? So, sorry, I had PI here. And I can be either 0, 1. So there's something I skipped yesterday, and I just realized that when people start asking me questions after the lecture, which is, well, I think I managed to convince you that the L0 version of this problem is inefficient. That's hard to do computationally. You have to try, well, you have, as I said yesterday, you have to fight against combinatorics. You have to try vectors beta with many different supports, so it takes a long time to do compute. And there kind of algorithmic barriers coming from computational complexity theory, which strongly suggest that this really is a hard problem for I equals 0. What about the L1 problem? So I should have mentioned this yesterday. Right? Why is the L1 problem computationally efficient? Why is it a good problem to solve? And there's a reason which is related to linear programming, and it's actually kind of it's a very standard conversion. But let me say quickly what linear programming is. So let's say you're given a vector in Rk. You're given a matrix B in Rn times k, and a vector B in Rn, and you have a linear program would be something like this. So it would be minimize the inner product of C and X subject to X being a vector in Rk, B times X being equal to the vector B, and the coordinates of X being non-negative. This is not necessarily the most general linear program there is, but it is general enough for our purposes. So what I'm trying to do here in the linear program is to minimize a convex function, a linear function, subject to linear constraints of this form. So B must solve some sort of system of equations, some linear system of equations. And I also require the coordinates of x to be non-negative. And this is a class of computationally efficient problems. And what do I mean by this? Well, there are many different ways in which you can put this. I mean, first of all, that you can prove that there are good algorithms that solve this problem in polynomial time. And polynomial here means in the number of bits you need to represent the matrix B, the vector B, and the vector C. So it's a problem, and there are algorithms which, even though don't have such good theoretical properties, they work very well in practice. So even for very large systems, even if K and N are very large, you can solve this pretty quickly. Well, if they're not too large, you're probably going to use this so-called simplex method. If they're larger, you're going to use interior point methods. But anyway, it's a problem that's been very well studied. Even more general variants where you have a general convex function here and convex constraint here are also very well studied. So this is good. Right? If you're able to write your problem as a linear programming problem, and then that's good for solving things in a computer. But our problem over here is not exactly a linear programming problem, right? So for I equals 1, what we're trying to minimize is not a linear function, right? It's it's a sum of absolute values here. Even though I claim that somehow P1 is a linear programming problem, that's not entirely obvious because you have this thing here. And we also do not have any constraint that says that the coordinates of beta must be non-negative. So how do you do that? Well, that's actually simple. So there's a kind of a natural way to move from beta to x. So beta is a vector, right? So each coordinate of beta has a positive part and a negative part. So in order to have a vector with positive coordinates, I'm going to take k, right, the dimension of x, to be 2 times p. And I'm going to write x is going to be, well, first you list the positive parts. And then you have the negative parts. This is not a one-to-one mapping because, for instance, if you add a positive constant to all the coordinates of x, you get the same beta back, right? But we're going to see that doesn't matter too much in the end. But so in any case, if you're given an x with no negative coordinates, you can find a beta. If you're given a beta, you can find an x. The mapping is one-to-one, is injective in this direction, not in the other. But we're going to see what we do about this later, right? Well, just for simplicity, let me write the vector beta as a vector of positive parts and a vector of negative parts, right? So this means I'm taking a positive part of each coordinate of beta. And here I'm taking a negative part. So what are my constraints, right? So, well, the way I wrote x guarantees that it has no negative coordinates. But I need to relate this constraint that beta solves the system to some other matrix here. That's also not very hard. So what you want is that alpha beta equals y. So it means that alpha beta plus minus alpha beta minus equals y. And now how do you write this in terms of x, right? Well, it's actually not difficult. What you do is you define this matrix B here, which, well, remember that now are dimensions twice the original dimension, right? So our matrix B, it's going to have, well, P columns, then P more columns, and N rows. And here you write down matrix A. Here you write down matrix minus A. So that's what you need in order to get the positive part of beta with a plus sign and the negative part with a minus sign, just like what I wrote over here. So the new constraint becomes beta x equals to y. So this is going to be the vector B. And what is the objective function, right? What are you trying to optimize? Well, the L1 norm is the sum of absolute values, right? The absolute value is the sum of the positive part and the negative part. So the objective function is just the, well, you're trying to minimize the sum of the coordinates of x. I mean, again, what I'm saying here is that if you look at the sum of the coordinates of x, you're going to get exactly the sum of the absolute values of the coordinates of beta under this transformation, right? And this you can write down as an inner product, right? It's the inner product of the all ones vector with x. So this is a linear programming problem. And as I said, so whenever you have a beta, you can transform into an x. The constraint is changed like this. And you have a new objective function. And now we must come back to this issue that I described before. I mean, is it clear that if you find the right x, you can find beta, right? And I claim that the answer is yes. And here's the reason. So essentially, I mean, when is this transformation not one-to-one? Right? I mean, I'm not giving you full proof of this. I'm just giving you an idea of why this works. So the main question here is, when is this transformation not one-to-one? And there's actually one way in which you make it one-to-one, not being one-to-one, which is if you add the same value to all the coordinates of x, you still get the same beta back if you're trying to invert this. Right? However, let's look, right, you have this problem here. So essentially what I'm saying is that if let's say I have a linear map going this way here, which takes x to beta. And this linear map has the following property. X, if I add a multiple of the all ones vector, right, the vector I have over there, it gives you the same result. Actually, I mean, so this all ones vector is in the kernel. There are more vectors in the kernel. Actually, a vector that has a 1 here and a 1 here is also going to be in the kernel. Right? So that's essentially the issue. However, there's something you can quickly realize, which is the following. So let's look at the optimal solutions, right? So let's say you found an optimal x. So an x that satisfies this has no negative coordinates with the minimal sum of coordinates that you have here. My claim is that, in fact, you can ensure, for instance, let's look. You want to get the beta back from x, right? So maybe you look at the first coordinate here, and you look at the corresponding coordinate over here. Right? This should be the positive part of beta, and this should be the negative part. And I claim that one of these is going to be 0, always in the optimal solution. Why? Suppose that, say, both are larger than 0. So say this one equals c, and this one is even larger than c. Now what can I do? I can subtract c from here and c from here. This is going to reduce the value of the function I'm trying to minimize. And you can check that just because of the way the matrix B is, that this new x, right, this x tilde, is still going to satisfy this. So what do I mean by what am I saying here? I'm saying that if you take two coordinates that correspond to the same coordinate of beta, say to beta 1 plus and beta 1 minus, and you look at an x that achieves this minimum here, then it must be the case that of these two coordinates, one of them is 0. And again, what's the rationale? Well, if both are not 0, you can subtract the positive value, make this smaller, and keep everything else unaltered. So you have a solution with a smaller value of the inner product here. That means that your previous solution wasn't minimal, right? So but we assumed it was minimal, so it's a contradiction. So it turns out that by magic, in some sense, that when you try to move from x to beta, but you only look at the optimal x, so you're guaranteed to get a corresponding beta. There's no issue of not being able to go back. Right, so but this is just a very kind of rough explanation of why this works and why this L1 optimization problem is a linear programming problem in disguise. Right? So this is the reason why this L1 method is efficient. And now we're going to go back to the things we were saying yesterday. So at some point we decided that we look at something like, well, you had beta hat solution of P1. We showed that the difference between the beta hat and beta min belong to a certain subset of vectors, which is a subset of all vectors whose L1 norm outside of a set S is less than or equal to the L1 norm inside the set S. Right? And S is just the supportive of beta min, meaning it's the set of non-zero coordinates of beta min. So yesterday we showed this. And let me mention that we also showed that whenever you have a vector in the set, if you look at its L1 norm, it's going to be, okay, let me say that little s is just the size of S. So if you have a vector in this set, it must satisfy the inequality. Must be the case that its L1 norm is less than twice times square root of S times the L2 norm. And now, and then we argued something, which was that if the kernel of A intersection CS1 only contains the zero vector, then delta hat must equal 0, which means that beta hat must equal beta min. Right? So again, so we know that the, delta hat is a vector in the kernel of A. We know it belongs to the set. So if somehow we can show this, then we know that delta hat must be equal to 0. And that means that beta hat equals beta min. It means that any solution of P1 is equal to beta min. So in particular, there's only one solution. Right. But as we said yesterday, we're actually not going to prove that a random A satisfies this, so we're going to prove something stronger, which turns out to be important for other applications. And and actually, let me list here the things we're going to prove. I'm not sure I'm going to list them in the same order as in the notes, but we're going to prove 3 things. So right, I forgot to say what kind of matrix I want. So I want A hat n. Well, I mentioned it yesterday, but I want a matrix with IID normal 0, 1 entries. belonging to Rn times P. And I divide it by square root of n, for reasons that will become clear later on. Right, so we're going to prove three things. So let me state here a property that a matrix might satisfy. That for all vectors in Rp of L0 norm less than D, you have that ax squared is greater than, say, a norm of x squared over 2. Right, this, I'm not saying, well, this is something that a matrix may or may not satisfy. That it behaves well, in some sense, over all sparse vectors. Right? So our first lemma is that A hat n, the probability that A hat n satisfies this property here, H1, is very close to 1 if n is larger than something like d log p times a constant. And what I mean by a constant that doesn't depend on d or p. I mean, you can actually do more here, but this is sort of enough for our purposes. Now, this is a random lemma, right? We're going to use probability here. And actually, this is the last lemma we're going to prove. But here's something, a second lemma, that if a matrix A satisfies H1, then for all x belonging to CS1, we have that AX, oh, sorry, I need to be a bit more specific. I need a slightly stronger property here. We're going to show that for you have this, well, okay, if A satisfies x1 with d greater than 1 plus 16s, then you have this thing here. So look, the first statement is probabilistic, right? So I'm saying that with high probability, this matrix A hat n satisfies this property over all sparse vectors, as long as sparse means that the L0 norm is less than n divided by log of p. That's essentially what this is saying. The second lemma is deterministic. It's just saying that if a matrix satisfies property H1, then with a certain value of d that's sort of like S, I mean, it's S plus a constant times a constant or something, then we know that this matrix A is good over the set CS1. So it satisfies this property. And of course, this implies that the property that we wanted, right? So that the kernel of A intersection CS1 equals 0. Why is that? Because take a vector in here that's not 0. So the norm of A times x is going to be larger than the norm of x times some constant, which is greater than 0, right? So what I'm saying is that if you take any vector in CS1 that's not 0, this inequality here implies that it's not in the kernel. Right? So these two lemmas together, they're sufficient to prove, right? So here you should, if you want to take this d here, you should take this to be 1 plus 16 times s. So these two lemmas together they imply the following. Well, if you take n larger than this, then with high probability, your matrix A hat n will be such that the kernel of it, intersection CS1, is just the 0 vector. Therefore, we know that the P1 problem is only going to have one solution, which is a vector you wanted to find. Is this clear? I mean, is the logic clear here, the implications? Again, we're going to say, well, we're going to prove that A hat n satisfies this property. And then we have a deterministic statement saying, well, if A hat n satisfies this property, it's good on all vectors in CS1. In particular, kernel of A, intersection CS1 is just a zero vector. And we know this is a sufficient condition that ensures that the P1 problem only has one solution. Right, so we're going to start. Let's see what time it is. Oh, we have plenty of time. Right, we're going to start with the second lemma here. And actually, it's the lemma is a bit weaker than, I mean, the hypothesis of the lemma is a bit weaker. Right, so let me restate lemma 1, lemma 2 here. Right, so you have a matrix in Rn times P such that for all x in Rp, so you need two assumptions. You need, well, first of all, you want a lower bound for sparse vectors. Where C here is just some positive number. Okay? So in this case, we know that you can take C equals a half. The second assumption is that if you take any canonical basis vector and you apply A to it, this is going to be less than M for some constant M. And then the conclusion of the theorem is that for all x belonging to, I'll say CS1, right, if the size of S is going to be equal to little s, again, so you're going to, for all x in the set, you're going to have ax squared larger than C minus 2s divided by d minus 1 x squared. And now we're going to see what this means. I mean, in our case, what we're going to do in our case, right? So if you assume this property H1, well, first of all, this first part here is satisfied, right? So you say, well, under H1, if you take a d-sparse vector, you have a lower bound with a constant that equals a half. And, right. And then, on the other hand, so how large can this be? Well, take a canonical basis vector here of A times EI. This is going to be less than 3/2 times the norm of EI, which is 1. So you can take M to be equal to, oh, sorry, there's an M here. And, yeah, 3/2. And then, well, in the end, we'll be interested in taking D, which is equal to 1 plus 16 times S. And what does this imply? Well, you're going to have here that this is 1/2 minus, well, 2 times m, which is 3/2, which should be 3 times s, divided by d minus 1, which is just 16 times s. And this should be greater than 1/4. Actually, you could take 12 here and be fine. This is the 1/4 that's going to show up here. So essentially what this, we can say like this. Well, I tried to argue yesterday that the set here, well, the vectors in here do not need to be sparse, but they're a bit like sparse vectors. In this case, what we have is this. So if A is acts well on sparse vectors, and sparse here means a little bit less sparse than S, right? But not much more. And it also, if A doesn't make the canonical basis vectors too large, then knowing these two things is enough to ensure that A behaves like we want it to behave over the set CS1. So again, what we're doing here, we're just, the lemma is just, the lemma I'm going to prove is just this statement here with no orange. And let me maybe, I'm going to call this constant here. It's going to be C prime. So under our assumptions, you can take C prime to, you can show that C prime is greater than 1/4. So this, the statement of the lemma is here. This is how we're going to apply it. We're going to apply with, because under property H1, which is what we're going to prove, we're going to have that C, you can take C equals 1/2, M 3/2, and D like this, and then everything works. Right, so how do we prove this lemma here, this lemma 2? Well, I should first of all say that this lemma is a purely deterministic statement, right? I mean, I'm just saying, if a matrix has these two properties, then it has this other property here. But we're going to prove this lemma using probability, in some sense. But, well, let me begin with the part that's not probability. So what we're, no, okay, no, sorry. This first part is precisely where we use the probability, but I mean, I'm still stating things that do not use probability. So this first part says this. So if you take a vector of norm 1, of L1 norm 1, then under the assumptions of the theorem, you get this thing here. So this is the first step in the proof, right? I mean, if you consider a vector that doesn't have norm 1, it suffices to divide by the norm on both sides, and you can see what happens. But for now, for the time being, you're going to stick with vectors with norm 1. So this is going to be kind of the crucial step in making the proof work. Right, so how do we prove this? Well, it's a bit of a funny proof. I mean, for some of you might have seen proofs using the probabilistic method in combinatorics, say, where you want to prove a theorem about graphs, and what you do is you prove it using probability, even though the theorem doesn't say anything about probability. You just use random constructions, and this is what we're going to do here. Right, so, well, okay, so let's fix some z. What we know about z is that these guys here, the coordinates of z, if you take the absolute values, they're equal to 1. They sum to 1. right? This is just a fact that has L1 norm 1. So I'm going to call these numbers here alpha I, just because I want to. But, well, actually I'm going to call them PI, because that's what I called them in the notes. It's sort of confusing because there's another P here, but PI is different from P, okay? And I just want to keep it the same as in the notes. So what you can see is that the numbers PI, they're greater than 0, and their sum is 1, right? So you can think of them as a probability distribution over the numbers from 1 to P. I'm just saying, well, if you have no negative numbers whose sum is 1, they're probability distribution. Okay, no big deal about this, right? So the vector Z is a sum of PI times a canonical basis vector times EI, where epsilon I belongs to plus or minus 1, right? Well, so certainly Z is a sum of canonical basis vectors, right? It's a sum with coefficient ZI here. So this is the absolute value of ZI. I just take the sign of ZI here to make this work. Well, if ZI is 0, it doesn't matter what you choose because PI is 0. But you can certainly write Z down as this. So now notice the following. Let V be a random vector, well, defined on some probability space. Okay, no, let me write this here. Let V1 up to VD be random IID random vectors. In RP, defined so that for all I between 1 and P, you have that the probability that V1 equals epsilon I, EI, is PI. So what this is saying? Well, when I choose V1, I'm choosing a random vector. And I'm going to say that with probability P1, this vector equals epsilon 1 times the first canonical basis vector. With probability P2, this vector equals epsilon 2 times the second canonical basis vector. And the same for all other possible choices. Right? I haven't done anything illegal here, right? So everything is well defined. This is just some discrete probability distribution in RP. I can take D random vectors with this distribution. Right? Okay. Well, let me note what's the expectation of, say, V1. Well, how do you compute the expectation of a vector? If it only takes finitely many values, it's very simple, right? It's the same as when you compute the expectation of a random variable that only takes finitely many variables. Well, you take a sum over all possibilities, have the probability of the ith possibility, times the value you get. And what is this? This is Z, right? It's written over there. So now, if we define V to be the sum or the average, actually, you can take just the sum of these vectors. Well, it's the sum of IID vectors, right? And for us, the main thing is that the L0 norm of V is always less than D. Why is that? Because vector V1 only has one non-zero coordinate, right? You're picking which coordinate you want to put in. So vector 2 only has one non-zero coordinate. And the same with 3. And you have a sum of D vectors, which are basis vectors, essentially, multiplied by signs, right? So this sum is only going to have at most d non-zero coordinates. Well, I mean, as we said we already said yesterday that if you have a sum of vectors, the L0 norm is subadditive, right? So you can apply this here. The L0 norm of V is at most the sum of the L0 norms, but the L0 norms of the individual terms are all 1, right? Because you have this. Right, so what do we have here? We have the following. So V is a sparse vector, and that means that if you look at A times V and take the norm squared, this must be larger than CV squared by assumption, right? So this is assumption A here. And now we're going to expand this, right? So what do we have here? We have that V inner product A transpose A, V is greater than C times V transpose V. And V is a sum, right? So I'm just gonna write this down. I'm just gonna write this in terms of sum over L and R going from 1 to D. VL transpose A VR is greater than C times sum over L and R equals 1 G VL transpose VR. Right? This is okay, right? So haven't done anything illegal again, right? So it's I'm just saying we have a sparse vector. Well, it happens to be a random vector, but it's always sparse. It has an L0 norm less than or equal to D with probability 1. So you can do all of this. But now we're going to use the randomness. And the way you're going to use the randomness is just to take expectations on both sides, right? If you have a random variable that's always larger than another, the expectation of the first one is larger than the expectation of the other one. Right? So I can take expectations on both sides. Right, so, and of course this expectation of a sum is a sum of expectations. So I'm going to compute the terms in the sum. And I'm going to start with, so I'm going to take each term in the sum and each term here and compute the expectation. So let's start with the case where L is different from R. What's the expectation of VL A transpose A VR? Well, if you really wanted to do this carefully, you'd have to be careful. But we're going to sort of, we have done things like these before, where we wanted to take expectations of expressions involving vectors, and somehow the general principle is because it's just this, that because the inner product is linear, and all the operations here are linear, you can always, if you have an inner product, the expectation of an inner product is somehow the inner product of the expectation. Well, not quite, right? Because this is not linear. We have two random variables here, two random vectors, VR and VL. So it's a quadratic expression. But these two guys are independent. So the same rules that apply to products of independent things apply here as well. Meaning the following. So because VL and VR are independent, right? Remember that the vectors are IID. I have this thing here. And then you need to check, but it's really simple. So, and this we know what it is, right? So this is Z, And the same thing, it's even simpler when you take the inner product of VL and VR, which is what you have here. So you have Z transpose Z. I'm just saying, well, because these two vectors are independent, the expectation of their product, or rather their inner product, is just the inner product of the expectations. Therefore, you get this. Right? So you're strongly using the thing that we proved before, just this thing here. Now we've got to consider the terms that are remaining in the sum, which are the terms with L equals R. So for L equals R, we're not going to use kind of an argument like this. We're just going to write down the expectation explicitly, right? So when I look at the expectation of VL inner product VL, I'm just going to say this is greater than 0. Okay, I don't want to care about these guys. Now I got the expectation of what is it called? Yeah, VL inner product A transpose A VL. So this I can write down explicitly, right? So it's just a sum over probabilities, the PI. With probability PI, this vector here equals EI times a sign. Right, so you get epsilon I EI transpose A EI times the same sign squared here. But the sign is just plus or minus 1, right? So this is going to disappear. PI. What is this? So this is the inner product of AEI with AEI. So this is just the norm of AEI squared. And remember, we assumed, right, part B of our assumptions is that these numbers are bounded by M. So the sum's at most M because here the coefficients add to 1. So what do we conclude from all this, right? So it's an elementary argument, but it's a bit long. Right. So let's go back to this thing here. We can now evaluate or upper bound all the terms that appear here. Right. So on the left, what do I have? I have a sum. So I have D times D minus 1 terms in which L is different from R. Right? And each one of those terms gives me Z transpose Z, which is just the norm of Z squared, right? Well, there is a coefficient there, C, which I forgot. And then there are D terms where L equals R, but we don't want to care about them. So I'm just going to forget. On the other side, I have D times D minus 1 terms. Well, what you get is Z transpose A Z plus D terms, which are like this. So they're bounded by M. So all we need to do now to obtain this inequality 1, well, divide by d times d minus 1. And we notice that here we have the norm of a times z squared plus m divided by d minus 1 is greater than c times the norm of z squared. And this is precisely what we wanted to prove here. Right? So now we want to get, so this is the end of the proof of 1. So now we want to prove that for x belonging to CS1, that a times norm of x, so this is the original goal, is greater than c minus 2sm d minus 1 x squared. So if x is 0, this is okay, right? Because, well, 0 is greater than 0, greater than or equal to 0. So let's assume that x is different from 0. So I'm just going to take z to be equal to x divided by the L1 norm. And what do I get? Well, I get that ax squared divided by the L1 norm squared is greater than c, I'm just using 1 here, right? I get cx squared, norm of x squared, L1 norm squared, minus m d minus 1. So I can multiply both sides by, okay, no, I have to divide by the, no, this is fine. I can multiply both sides by the L1 norm squared, so I get this inequality here. Right, and how do I get this? These two things are very close, right? I have this and I have this. So the only thing that's missing now is something we already know. We know that when x belongs to the set, we have an upper bound for the L1 norm. The L1 norm is at most 2 times square root of s and times the L2 norm. So, which means probably I have the constant wrong here, because I need to take the square of 2 here. Okay, so I want to prove a different inequality, and maybe I'll have to change something later. Oh, that's fine. Yeah, I had a 3 here, but that was a mistake. Now I remember. Oh no, I had a. What did I have? Okay, whatever. Well, I have to fix the constant maybe. But in any case, why does this 4 show up here? I'm just going to use the fact that we saw before that for the L1 norm of x is less than 2 times square root of s times the L2 norm. So if you, without the square, if you square this, you get here 4 times s times m divided by d minus 1 times the L2 norm. So it's exactly what you have over here. So I mean, in the end, what we're showing is something like this. So if you can prove a statement like this, so that A is lower bounded by the L2 norm minus something like the L1 norm, and then this is enough to imply that A is lower bounded over all, just by the L2 norm, over all vectors in CS1. Okay, maybe this is going too far. I mean, we're not going to need this, but what I will just mention is that even, I mean, for more general problems, I mean, there are other variants of compressed sensing and lasso methods in statistics and many other things for which you cannot always guarantee that the optimal solution is sparse. And sometimes you know really nothing about it. And then what you do in order to analyze those variants, I mean, what you can do is just you stop the analysis here somehow, and you use this inequality instead of saying, oh, because I have a vector in CS1, I can do more, right? But even this inequality by itself is already fairly useful in some settings. Right, so what have you achieved here? Maybe I should rewrite the statement of the theorem just to keep it on the board. And I'm just going to write it in the way with the constants I need. Right, so what do I need D to be? M is going to so get 12, no, 6. Okay, annoying. I guess this is the right constant. I had 16 here before, but this is the right constant. Right, again, so we have a deterministic statement. Now I just wrote a version of it with the constants I'm going to use. I'm sorry there was an error with the original D. So I'm saying, well, define D like this, right? Well, remember that little s is just the size of the set S here. So define D like this. And now assume that your matrix is such that if you take a D sparse vector, norm of a z squared is larger than half of the square norm of z. Moreover, assume that for all canonical basis vectors, the norm of a ei squared is less than 3/2. Then you get this inequality here for all the vectors in CS1, which, as we said many times, is sufficient to prove right, that the L1 problem has a unique solution. Right, so now we're now going to get back to a random problem. So we're finally going to use probability. Well, we use a little bit of probability here just to prove this theorem, right? This fact here. And now we're going to use probability in a more substantial way. We're going to use what we did in earlier in the course. So not that early, right? Essentially what we did yesterday for covariance-type matrices. Right, so again, what's the random matrices we're going to use? They're of this form. You take IID, normal, 0, 1, standard normal coordinates. You divide my matrix by the square root of n. I mean, the reason why we divide is not entirely clear. Maybe because, we just have a linear system. So if you divide a matrix on one side, you're going to divide the vector on the other side. It doesn't matter for the linear system whether it has a unique solution or not. But it turns out that dividing here is more convenient for the analysis. So I'm just going to keep it like this. Right? Well, there's a different way to write this matrix. It's just to say that this is a matrix of the form 1 over square root of n with row vectors here. So this is why they're transposed. And these vectors, they belong to RP and are standard normal vector. They are standard normal vectors in RP, and they are IID. What? So what's a standard normal p-dimensional vector? It's a vector with p coordinates that are independent normals. Right? So here I'm saying the rows are independent, and the entries in each row are independent. So I have the same distribution. I mean, it's nice to write it like this, because then you can say that alpha hat n equals 1 over square root of the following sum. And there's nothing really special about this. I'm just saying, well, the rows of your matrix are these vectors, x1 transpose up to xn transpose, and this is the form that the matrix has. Now, there's something nice about this form, which is when you take alpha hat n transpose alpha. Okay, why do we want to take this? For any RP, if you take the norm of alpha n x squared, which is the kind of thing we want to consider in our analysis, right? What is this? Well, it's very simple. It's this is just x squared alpha hat n transpose alpha hat n x, sorry, not x squared, x transpose whatever. And this is going to be exactly this. So it's the same kind of covariance type matrix that we considered before. I mean, this is just a matter of writing things down. I mean, what is alpha n times x? Well, in order to get this vector, you take the inner product of x with each one of the rows. Right? Now, when you take the norm, you're going to look at the squares of these inner products, which are over here. And we know that we have this correspondence here. Right? So and we even have results that we saw in the previous class, results that told us the following. If you look at the operator norm of these two matrices, the difference here, right? This is small with high probability, if n is much larger than p. What we saw more precisely is that if you want to make this norm less than epsilon, you take n to be of the order p divided by epsilon squared plus something which ensures that the probability of this happening is very high. Right? So, okay, here's a precise statement. That the probability that the operator norm is greater than epsilon is less than delta if n is larger than 16 over epsilon squared, p plus, there's some constant here, plus log of 1 over delta. This was a theorem we proved last class. I don't remember what the value of this number is, but it's something. It doesn't matter too much what it is, because we only care about orders of magnitude. I mean, the important thing to notice right now is that we're kind of in a strange situation, because if we knew this, if we knew that this operator norm was small with high probability, then we'd be able to guarantee these two things with high probability, right? So if, right, what do I have here? I have alpha hat n z, which is just z transpose sigma hat n z. So if sigma hat n is close to the identity, then I'm certainly going to get this kind of equality. If sigma hat n is close to the identity, I'm also going to get this kind of inequality. So it would be very nice if we could prove that this event here has a small probability, meaning that the probability that the operator norm is small is large. It's close to 1. That would be very nice, but it actually doesn't work. Because, remember that the setting that is of interest to us, this was here somewhere a while ago, right? We're precisely interested in the setting where n is much less than p. And we already said that many, many times, so I hope you remember, that what makes this problem interesting that we're able to solve a linear system that has less equations than unknowns, right? So it's, by itself, this is not sufficient for us. But we're going to do something else, because this is actually much more than what we need. We don't need the matrix sigma hat n to be close to the identity. We need something much easier, right? Well, much easier, we need something much less demanding. So, and here's what it is. So let's take okay, let's look at a subset D of the coordinates which has little d elements. Okay? You can define a projection operator which takes a vector x1 up to xp and projects it to the vector. Well, you just keep the coordinates that happen to be in D. So let me write it like this. You're taking the span of the canonical basis vectors indexed by D, and you're projecting onto that span. It's just the orthogonal projection. And because you're using the canonical basis, this is a diagonal matrix. The transformation here is given by a diagonal matrix. Right? Now my claim is the following. Now let me write it like this. If you have that for all D of size little d, sigma hat n, well, you compose with the projection. If this operator norm here is less than 1/2, then properties 2 and 3 over there both follow. So in other words, I don't need to look at the whole matrix sigma hat n over which I have no control, right? And I have some degree of control, but I can't say much about, say, the spectrum of this whole matrix. Well, actually, I can say a few things, and they're all bad, right? Because if you take, for instance, n to be less than p, then we know that this is a rank p matrix. This is going to have rank at most n, which is less than p. And it certainly means that sigma hat n is far from the identity. But nevertheless, if I know that those d by d blocks of the matrix behave well, they're close to being diagonal, then that's enough for our application. And why is that? Well, we just need to look at what's going on here. I'm just going to prove property 2 right? And I'm not going to do anything about property 3. But it's even easier, so it's no big deal. So if you have a vector with d or less components that are equal to, they're different from 0, then we know there exists a subset of coordinates. I mean, this is really almost a tautology, right? There exists a subset of d coordinates such that z equals pi d of z. Right? You're just saying, well, if you take all the coordinates of which z is non-zero, maybe add a few, and then you're sure that the projection of z will preserve it. You're not killing any non-zero coordinates. Right? Now, let's assume that you have this thing here. Right? So let's. So notice that if you have this a hat n z squared, it's just z inner product sigma hat n z. This is just, well, you can just place the projection operator here. Right? This is just saying, well, multiplying z by this projection operator doesn't change it. Right? Is this okay? And now you can say, well, this is larger than z pi dz minus norm of z squared times the operator norm. And of course, this is the norm of z itself, right? Precisely because when you project z, it doesn't change. Whereas this, well, this is at most a half, right? So just using the fact that these projected versions of sigma hat are close to the projectors, that the d by d blocks are nearly diagonal, you can prove this property number 2 here. And the proof of 3 is even simpler, right? This is also sparse vector, so it's going to work. So this is why the claim is true. But now, the nice thing about the claim is that, as I said, you're not looking at the whole matrix. You're just looking at d by d blocks, right? Let me make a claim here, another claim, which is the following. Now let's see if you understand what I mean. I'm saying the following, that instead of looking at the whole matrix, you look at a d by d block, then you can replace the dimension by d here. Instead of the full p dimensions of your whole space, you just care about a d-dimensional subspace. Is that clear? I mean, so why is that the case, right? So I mean, there's two ways to, at least two ways to see it. So here you have your matrix sigma hat n. Right, sigma hat n is something huge here, something huge. But you're saying, I want to look at this block here. And I want to prove that this block, so I make everything outside of this square here, I make everything equal to 0. And I want to prove that this is close to a matrix where I have a diagonal of 1s here, and the rest is 0. So it should be clear that you're not really computing, you don't really need to compute the distance between the full matrices. You just need to compute the distances between the blocks here. And the reason for that is that you have a decomposition for the whole space, and you have the vectors whose support lies in D, and you have the orthogonal vectors to that. And these matrices, they do not act on the orthogonal vectors. The orthogonal vectors are the kernel of both matrices here. So you just need to care about the subspace spanned by these guys. And this subspace is D-dimensional. So again, this is maybe not a full argument, but it is the argument. This is really the reason, right? Another way is instead of thinking of this as a linear transformation of RP, you think it as a linear transformation over the range of this operator, which is a D-dimensional space. So it's more or less the same idea. The main point is that in any case, you're looking at the distances between these two matrices, right? So it's a D-dimensional problem, but it's of the same nature, right? So if you look here, what is this matrix like? So it's so sigma hat D. No, sorry, pi D, sigma hat n, pi D is just a sum of this form. Right? Well, this is maybe not entirely obvious, but you can also think of it in the following way. When you take this block, it's like instead of looking at the full vectors xi that I had before, I'm just looking at the coordinates of xi that fall within the block. But that's also a Gaussian vector with IID standard coordinates. Okay? But in matrix form, this is what you have. This is a standard Gaussian vector in D dimensions. So you have this very nice bound, which we proved last class. And it's enough to prove that for a single subset here, right? I mean, here I say, if for all subsets I have this, then I'm finished. Whereas this is telling you, well, for a single subset, I can guarantee that the probability that, say, this is larger than a half, which is what we care about, is small, assuming that n is larger than some constant times d, blah, 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 whatever, right? Well, the constant here could be 64, I guess, because it's 16 divided by 1/2 squared. Okay, let me put 64 here. Just to be. But you need, again, what you need is you need to prove that the probability, so this is not the probability you really want to bound, is the probability that there exists a subset of D coordinates such that the norm is large. But we've seen already many, many times this argument, this idea of the union bound, which is the simplest bound you get on a union, right? So all of these events, they have probability less than delta. And how many events do you have? Well, you have P choose D, right? It's the number of choices of D coordinates that you can make out of P. And let me just say that this is less than delta times P to the D. Just the simplest possible bound on the binomial coefficient here. Right, so you want this to be small, right? So you need to take delta like something 1 over P to the 2D, let's say. Right, assuming P is very large. But this is okay, right? Because only the log shows up here. So this is going to be D log P, essentially. Oh, twice D log P. Okay, what is this saying? This is saying that if you take an n that is this big, then you can guarantee that the probability that there is some bad subset of the coordinates, some bad block of size D, is very small. We already argued that if all blocks are good, then we have the properties we need, right? We have 2 and 3. which imply that matrix A acts well on the vectors in the set, which implies that the L1, the basis pursuit problem, has a unique solution, which is a vector we're trying to find. So again, by taking n this large, you ensure that this property here holds with high probability simultaneously over all subsets of D coordinates. That implies that you have these two properties, which imply that the problem is solved. So L1 minimization finds you the original vector. So I think, well, I already said everything I have to say. I was a bit fast today. So do you have any questions? Is anything not clear here? I hand waved a little bit today just by saying, well, this is simple. You can just look at the blocks, and the blocks are Gaussians. But it's just, I hope that the main ideas somehow are clear, that you don't want sigma hat n to be nice over the whole space. You just want blocks of it to be nice. Because these blocks are d-dimensional, that becomes a d-dimensional problem. But you have many d-dimensional problems, right? You have p choose d d-dimensional problems. So you need this term here to make everything work. So in the end, you need n of the order of d log p, and d is of the order s. So you need n of the order s log p. So as long as the number of equations is like the sparsity parameter times the log of the ambient dimension, you're good. And this is not much, right? So, in principle, you needed n larger than p. Now you need n larger than log p times something. So it's much, much better. Questions? If there are no questions, just thank you for your attention. And tomorrow we have the lecture by Afonso, who's sitting in the back now. And he'll be talking about community detection.